Hello wonderful person, this is Anton, and today we're going to discuss one of the most fascinating substances in the universe, water. Something that sometimes we take for granted because it's literally sold in a store in a plastic bottle. But as it turns out, based on a lot of different studies, today we know that water on Earth is just a little bit different from how we usually find it on a lot of other planets, and of course, in a lot of other extreme conditions in outer space. And specifically under some of the most extreme pressures and temperatures found inside some of the most common planets, such as various gas giants, water stops behaving the way we usually expect it to behave and becomes something very, very bizarre. Instead of being a kind of a life-giving liquid like it is on planet Earth, it seems to become something extremely alien with some very strange, unexpected effects. And so in this video, we're going to take a look at some of the recent studies, and especially this one, from scientists at Sorbonne University, whose study now suggests that in some of these extreme environments, water transforms into a superacid, an actually acid that's much, much stronger than anything on Earth. With this intriguing discovery, potentially finally explaining the mysterious diamond rain mystery, or basically how some of these planets seem to contain diamond rain, and also explain how the magnetic fields in some of these giants seems to be generated. And here we're talking about planets like Uranus and Neptune. But in order to understand this, let's first define superacidity and basically discuss how this was discovered and what we know so far. Now by itself, this is of course not a new concept, because it's generally defined as any kind of an acid with acidity greater than 100% sulfuric acid. Something that I think most of us must have used in some kind of a high school experiment back in the days. But more specifically, it has to be some kind of a medium in which the chemical potential of the proton is higher than in pure sulfuric acid. And we actually do contain some of these on planet Earth as well. For example, something referred to as fluoroantimonic acid usually combines hydrogen fluoride and antimony pentafluoride that creates such a powerful acid that its overall strength is at least 1 billion times greater than pure sulfuric acid. So definitely not something you want to come close to. As a matter of fact, it dissolves pretty much anything, including various complex hydrocarbons, as if it was just made out of wax. And some of the initial discoveries in this field resulted in the Nobel Prize in Chemistry back in 1994. And while normally when it comes to these superacidic substances, today they're normally used in various petrochemical industries. For example, they're generally used on a massive industrial scale in order to upgrade hydrocarbons or to even produce high-octane fuels. Or basically some of the more expensive gas that you might use in your car is usually produced using these superacids, with additional uses usually involving some kind of an organic chemical experiment that tries to produce much more complex organic molecules with extreme efficiency. In other words, despite being kind of rare and extremely corrosive, these exceptionally potent chemicals definitely have at least some use. But in this particular study, instead of actually making it, researchers used some of the more advanced computer simulations in order to show that even water can naturally become an extremely powerful acid under immense heat and pressure conditions. And specifically, we're talking about temperatures of at least 1700 degrees Celsius and up to about 2700 degrees Celsius, and pressures between 22 to 69 gigapascals. And so basically temperatures that we can usually only find deep inside planet Earth, and pressures equivalent to approximately 100 elephants standing on the tip of your finger. And so under these extreme conditions, water molecules no longer stay the same and start to break apart or ionize much more frequently, which usually creates an extremely reactive environment dominated by hydronium ions. These are basically H3O ions containing an extra proton inside the molecule of water. And well, it turns out that this then leads to some really interesting conditions, including what's known as diamonds in the sky. This is actually a kind of a hypothesis based on a lot of different studies that suggested that many of these planets do contain literally diamond rain in the sky. And in this case, this study does provide some intriguing evidence. And that's because for many years, scientists suspected that methane, which both Uranus and Neptune contain in huge amounts, most likely breaks down into pure carbon as it travels downwards into extreme pressures and temperatures. And this carbon then crystallizes, which as we know from planet Earth, tends to basically form diamonds. But the exact chemistry of how this happens in the mixture of water and methane was not actually understood. And so in this new study, scientists reveal a kind of a three-step process. First, protonation. This superacidic water attacks methane, or basically starts to dissolve it, which then forces an extra proton to attach to the methane molecule and to create a kind of an unstable state referred to as methanium. This would be basically CH5. And these methanium ions are extremely reactive. They actually tend to quickly release the molecular hydrogen and then leave behind another ion that's essentially a kind of a reactive carbon-based cation. With the last step being condensation. These reactive carbon pieces then find each other and start to stick together, which basically forms much longer chains and eventually creates nanodiamonds. And while this particular process is quite similar to the process or the reaction discovered by the Nobel laureate George Olah. This is that Nobel Prize from 1994. He actually studied how hydrocarbons react in laboratory superacids at much milder conditions. And so in this case, this idea of superacidic water potentially explains a lot of extreme chemistry inside various ice giants and many different gas giants, but more importantly for planetary studies, now potentially provides us with an explanation for their somewhat strange magnetic fields. And that's because usually we think of these magnetic fields as generated by the movement of some kind of an ion or some kind of a charged particle inside the water layer. But this study shows us that carbon from methane actually participates in this proton exchange, which means that carbon is actually contributing to the electrical conductivity and then directly influences the shape and the strength of the magnetic field, creating some unusual shapes as observed by the Voyager probe back in the 1970s. And so here this potentially explains the strangest of the magnetic field and some of the more unusual types of precipitation inside various planets. But obviously when it comes to water, this is not the only strange thing it seems to be able to do, because in a lot of other conditions, water becomes even more bizarre. For example, in some conditions, it can also become what's known as a supercritical fluid, something that was also analyzed in this particular study not so long ago. And that's a state where the distinction between a liquid and a gas tends to disappear. And so when heated more than 370 degrees Celsius and at pressures of about 220 bars, water is no longer liquid or gas. It's something in between. Or basically it starts to act as a kind of a very, very dense, weird vapor substance that can even pass through solid materials like a gas would, but at the same time can still dissolve other substances like a very powerful liquid. And so in this particular study, scientists wanted to understand, okay, so first of all, how does this work and what exactly happens in these conditions? And specifically, they wanted to find out if it was because of the hydrogen bonds. Because we know that hydrogen bonds are responsible for pretty much most of the unique properties of water on Earth. And so just as scientists suspected initially, in this supercritical phase, when the water starts to behave very differently, hydrogen bonds basically completely disappear. And so instead of an organized network connected through the hydrogen bonds, all of the water molecules are now in a state of random encounters. They tend to rotate very randomly and very fast, and never stay together long enough to form any real bond, which basically makes the supercritical water an extremely powerful solvent that we know potentially exists in some very extreme conditions in the oceans on Earth, specifically the very important hydrothermal vents that have now become the main target for studies involving the potential origins of life. In other words, there's a very high chance that one of the main reasons life might have started here is because water around these hydrothermal vents tend to kind of switch back and forth between supercritical and regular states, which might have contributed to the formation of early life. Okay, cool. But water gets even stranger once you start going even deeper into planets. Because apparently it can also enter a state referred to as a superionic ice. And in this phase, the oxygen atoms tend to lock in place and create a kind of a solid, or basically start to behave as ice, but hydrogen atoms, or the protons, start to flow through this ice just like a liquid. And so it's a substance that's effectively both solid and liquid at the same time. This usually happens when the temperature is in thousands of degrees Celsius and millions of atmospheres of pressure. So literally somewhere in the center of Neptune and Uranus. And though we're not entirely certain what effects this produces, based on a lot of lab experiments, This state seems to definitely exist and very likely create some really strange crystallized surfaces inside those planets that I guess to some extent resemble a kind of a very hard terrestrial surface. But intriguingly, in certain planets, the ones that don't actually have enough pressure and temperature, water can also turn into some other states of ice we've discussed previously in some of the videos in the description, such as the plastic ice known as Ice 7. This usually happens at 60,000 times Earth's atmospheric pressure and above 327 degrees Celsius. And here this actually forms a kind of a cubic ice where the molecules can easily rotate in place. And so instead of basically being rigid solid ice like what we have on Earth, here we get a kind of a malleable ice that can be squeezed, bent, and folded. This very likely exists on a lot of different moons out there, and potentially also explains some of the anomalous effects we see from them as well. As a matter of fact, as of 2026, there are now officially 21 types of different water ice known to exist in different types of conditions, and the ones we've discussed you can find in the description below. But water also gets super weird if you try to make it do things at extremely small scales. And specifically, if you actually try to force water to go through very narrow space, such as a typical carbon nanotube, it also starts to behave completely differently to what's expected from it on a much larger scale. Here it starts to exhibit a superflow property, with water molecules actually speeding up under higher pressures, because they arrange themselves into these very unique single-file configurations and no longer interact with each other the same way. And so the molecular mobility increases dramatically, with these nanotubes basically acting as a kind of a lubricant, allowing the water to flow super fast, or essentially creating a kind of a superflow. And that's on top of some other discoveries about water that even today we have trouble explaining. Like, for example, it seems to behave slightly different if it's a little bit colder compared to if it's a little bit warmer. This is also something we discussed in the video in the description. And it also possesses strange viscosity anomalies compared to other liquids, because normally liquids under pressure actually get thicker or become more viscous, but water becomes thinner and starts to flow much easier if you start to raise pressure. Which essentially suggests that out of all different compounds and molecules known to us, water seems to be still quite mysterious and quite poorly understood. And though most of this research so far has only been based on computer simulations, in order to understand this, the next step has to be experimental evidence by essentially using high-pressure environments and extreme temperatures. Because based on all of this, the implications are huge. And this is not just in regards to space exploration or understanding how different planets work. Here, this could literally lead to some very effective industrial processes, just like what happened with the discovery of superacids. For example, there might be an industrial process for petroleum refining that produces way less pollution and can even help us synthesize materials like artificial diamonds without the use of hazardous chemicals. Because in this case, all of this would just use water. Extreme water, but water nevertheless. And so based on all of these studies, we are now pretty clear that water is definitely much more complex than we ever thought, and seems to transform into something unimaginable and extremely difficult to understand when pressures and temperatures reach certain levels. And so as of today, it's essentially one of the most mysterious substances, despite being so common and present in pretty much every star system and most planets out there. But on that note, once we discover something else, we'll come back and talk about this in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining the channel membership that grants you early access. You can also support this channel by buying a wonderful person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.